All right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at ionic solids. Now, ionic solids have some pretty characteristic properties in that they have a very low vapor pressure, they're brittle, they conduct electricity only when they're in their molten or aqueous states, and are also not very soluble in nonpolar solvents. So all these properties can be qualitatively explained using Coulomb's law and actually just taking a look at the general structure at the atomic level of my ionic solid, aka my crystal lattice. So what we're going to do is we're going to take a look at these properties one by one and refer back to this drawing that I've got here on the left. So the first thing that we want to take a look at is the property of vapor pressure. And with ionic solids, they generally have a very low vapor pressure, right? And so we understand that if we're looking at this ionic solid, that the attraction between the positive and negative is a Coulombic interaction, and it's between fully charged ions, and so it's very, very strong. And what this means, in order for vapor pressure to occur, one of these ions actually has to escape the solid state and enter into the gaseous state. Well, since the Coulombic attraction and the lattice energy of this solid is very high, the number of molecules that can escape actually ends up being very low. And so what we're going to summarize this is saying it's got a very high intermolecular force in the form of lattice energy, and so the vapor pressure is actually very low for our ionic solid. The next thing that we're going to take a look at is actually ionic solids tend to be very brittle. And so what brittle means is that it's going to break rather than bend. And so again, I'm going to take a look here at my ionic solid, and we have to notice that my positives and negatives line up with each other. So remember, when this crystal lattice is actually formed, my attractive forces are going to be maximized, my repulsive forces are going to be minimized, and it's actually going to arrange itself in the ionic solid so that occurs. Well, what happens if I were to take this particular part of the compound and actually push down on it? Well, you'll see as this one negative ion starts to shift down, it'll end up face to face with another negative ion. And that'll actually increase the repulsive forces so much because also in accordance with that, as this negative shifts down, so does this positive. And so what we end up with is these like charged ions are next to each other. The repulsive force is very high, and it tends to cause that solid to actually just break off. And so the brittleness of these ionic solids occurs because as those ions slide and shift past each other, the repulsive forces are increased and just causes the solid to break apart. The third property of ionic solids that we'll take a look at is electrical conductivity. And so remember, with electrical conductivity, we needed something to be mobile, some kind of charge to be mobile to transfer electrons from one place to another. Well, this is a solid. We do not have translational movement. And so the ions are not mobile. So the electrons in that particular case cannot be transferred. So as a solid, there is no conductivity with ionic compounds. But whenever I melt the solid, right? Remember, if I'm going to melt this particular solid, I'm going to separate all the ions away from each other, and then they'll be mobile in the liquid phase, because liquid phases have translational movement. Or when I dissolve them in water, right, the ions dissociate and again become mobile in that liquid environment. And when I have those ions that are mobile, that have translational movement, the electrical charge can actually be transferred from one area to another. And so the big thing with electrical conductivity is that solid ionic compounds, no conduction. They are not electrically conductive at all. But whenever we melt them or dissolve them, the mobile ions actually allow for that compound to conduct electricity. And then the last thing that we're going to take a look at is the solubility of ionic compounds. And we'll make the statement that ionic compounds are generally very non-soluble or insoluble in nonpolar solvents. Right? So ionic compounds generally insoluble in nonpolar solvents. And really it goes back again to this lattice energy. So we understand based on Coulomb's law that positive negative is an attractive force, right? And so the positive negative next to each other, if I were to have a nonpolar substance next to it with just LDF, that intermolecular force and attractive force between them would be relatively small, right? And not enough to overcome that lattice energy to actually pull the ions out of the solid state. And so that's why your ionic compounds are generally very, very insoluble in nonpolar solvents. And again, it goes back to this similar intermolecular forces interact with each other more strongly, right? And then the last thing I want to just touch on again before we leave, ladies and gents, remember that in this crystal lattice, the primary intermolecular force or the primary bond energy is going to be defined through lattice energy. And we want to make sure that we remember that, hey, the larger the charges on ions, the higher the lattice energy. Or the smaller the ionic radius, the larger the lattice energy, right? So bigger charges, smaller ions lead to a higher lattice energy, and we want to be able to relate that back to Coulomb's law and Coulombic interaction. All right? Well, that's it, ladies and gentlemen. So that was short and sweet. If you have any questions, I'll see you in tutorials for those. Otherwise, I will see you in class.